real-life diagnostics and debugging examples in the cloud. Asia Kamsky is affectionately known as our principal know-it-all. She has held multiple roles at MongoDB over the past 10 years, including as a developer advocate, principal engineer, principal solutions architect, and a principal product manager. Joanna is a senior engineer on the cloud engineering team at MongoDB, tasked with improving things for both customers and cloud team developers. Previously, she spent 8 years on the technical services team at MongoDB, helping customers around the world tune their MongoDB deployments for optimal performance. Please welcome Asia and Joanna to the stage.
And the crowd goes wild.
Good afternoon, everyone. Thank you so much for coming today. My name is Joanna.
I'm Asia. What are your names?
No, just kidding.
Yell them all out at once. We'll remember them. No, just kidding. We will not actually remember them. All right, so then in that case, I have a different question for you. How many of you here are or have been a developer? Oh my God, almost every hand.
Yeah.
Now I'm afraid to ask the other one. All right, how many of you have been a DBA or played one because nobody else wants to do it? You know, yeah, more hands going up now.
As soon as you said played one, more people stuck their hands
up. I've worked for startups my entire career pretty much, so I've pretty much worn both hats.
I've worked in technical services, helping customers solve problems for 10, 12 years now. Problems
I caused problems, she helped solve them, that kind of thing. Yeah.
It's a good partnership.
Yeah, good partnership. Let me ask you another question. How many of you, like when you were little and you were like dreaming that someday you would grow up, that you would become a DBA? Awesome, some hands went up. Yes. Yeah, well, you're probably kidding, because most kids don't want to grow up and become DBAs. Like when I was a kid, all my friends wanted to become astronauts or firefighters or ballerinas or famous. Not me. My favorite thing in the world was to solve puzzles. And I knew for a fact that when I grew up, I would be a detective, because my hero was Sherlock Holmes. Now, Sherlock Holmes was actually invented by an author, Sir Arthur Conan Doyle. And I don't know if any of you know this, but Conan Doyle was a physician before he was a writer. In fact, when he was in med school, he met an amazing man, Dr. Joseph Bell. And Dr. Joseph Bell was very famous for his absolutely uncanny ability to observe very minute, tiny details about things, people, and to draw seemingly far-fetched but very accurate conclusions. In other words, Joseph Bell was the inspiration for the character of Sherlock Holmes. And both our favorite detective and Joseph Bell were masters at diagnostic thinking. But what is diagnostic thinking, Joanna?
Right. Diagnostic thinking is a way of reasoning about a problem and to come towards the true cause. And we reason about the behavior that we observe, about our personal knowledge of the problem domain, the environment, and applying the diagnostic process to eventually come up with the true cause of a problem.
So maybe an example can demonstrate that. We had a customer, this was years ago, and while talking to them about something else, it turned out that they were restarting their MongoDB process nearly every day. And we're like, wait, why do you have to restart your MongoDB process nearly every day? And they said, well, because our MongoDB is using up all of the RAM, and we get an alert that like almost all of the RAM is being used, and the only way to get it to give back the memory is to restart it. And I'm glad to hear that a number of you are kind of chuckling at that, because what was happening, of course, is they were observing a behavior, but because they didn't have domain expertise, meaning they didn't understand the way that Linux handles the memory and how it allows the file system cache to use any memory that's not being used by other applications. They were observing facts, but they didn't have the knowledge or expertise to combine with that. And so they actually dreamed up that there was a problem where one did not exist. Now, normally, that wouldn't be the case. You would have the expertise. You would then observe that there's an actual problem, and then you'd need to solve that problem using the diagnostic process.
Right, so the diagnostic process is just a way of solving a problem, thinking about a problem, and coming up with a solution. So famously, Richard Feynman taught us how to solve problems. It was very easy. Step 1, write down the problem. Step 2, think really hard about it. Step 3, write down the solution.
That's it. Really simple. Thank you for coming to our TED Talk. Goodbye.
Just kidding. Just kidding. We're going to have to go into a little bit more detail than that about the diagnostic.
Turns out it's not as simple.
So the diagnostic process consists of 4 steps. Step 1 is to come up with a full problem description. Try and get as much data about the problem, about the domain, about the environment as possible. This will help you with step 2, generating some hypotheses about what you might think have caused the problem. Step 3 is then to just eliminate some of these hypotheses. Some of these hypotheses will be contradicted by other data that you know that you've observed or that you know about the system. The last step is to perform experiments to validate which one of these hypotheses is the true cause, which one is consistent with all of the data and all of the domain knowledge and could be the true cause of your problem.
That sounds really complicated.
It's not, though. Let's go through a different example. Let's go through something that has probably happened to all of you. My MongoDB is not running. So maybe first step is to gather some data, maybe ping the server, see if it's still running or not, maybe look at some metrics. So Atlas has many, many metrics available. One of them is the disk space free metric. How much disk space is still available? And we can see that this is the disk space free on the storage device that stores all data for all databases. And while there was some disk space free to begin with, that line has been trending down and is pretty close to 0. So that looks like a hypothesis for what our problem is.
No disk space.
No disk space. So what's next? We need to validate that hypothesis. So one thing we might do is
delete data.
Sure.
Oh, wait, no.
You can't really delete data if your MongoDB is not running, unfortunately.
Right, okay.
You could try, if this was on premises, you could try and delete some log files, and if you reach out to technical services, we can do that for you on your behalf for an Atlas cluster. But a better solution might be to increase the disk space, to increase the disk size.
Make a bigger disk.
Make a bigger disk.
Doesn't Atlas have some way of doing that automatically?
Yes, absolutely. Atlas also has a feature called autoscale. When your disk space when your disk becomes, say, 90% full, Atlas obviously is monitoring that and will automatically resize your disk to ensure that there is a suitable buffer of free disk space. Not so helpful at the moment because you're out of disk space, but maybe as you're increasing the size of your disk, you want to tick that autoscale button so you don't have to monitor it yourself. So if you resize your disk and there's now sufficient disk space free, I think we've confirmed the hypothesis.
Oh, if MongoDB now starts up.
If MongoDB now starts up, correct.
Cool, problem solved.
That's it. That's the entire diagnostic process.
Okay, so diagnostic process has 4 separate steps, but it sounds like the first step is most important because that's where you start?
Yeah, absolutely. And you have to start on the right foot to make this process a success. So the problem description is the first part. And you want to generate a full problem description. It's essential that you know as much about the problem as possible so you fully understand the problem, the environment, so then you can get a good mental model and that will help you reason about the problem and generate hypotheses. Make sure that you generate the problem description before you start generating hypotheses. It's very, very common, and I've fallen into this trap myself. You start hearing about a problem and you think, oh, it must be.
I know what it is.
It must be that.
I know what it is.
And then you start looking at data and you think, oh, yes, that supports my hypothesis. That one does too. You start cherry picking data and that is no good. As Sherlock Holmes said, it's a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts.
In fact, this was such an important concept. This quote in different formats appears in at least 3 different stories.
So the problem description at its heart consists of two parts, a what and a how. What is the object that has the problem? How is the problem manifesting? My MongoDB is down. My writes are taking longer than they used to. But that's not the only part of the problem description. We also want to know where it's happening. It could be happening in a specific data center, in a specific node. We need to know when it was happening. When did it start? Is it continuous? Is it ongoing? Does it only happen sometimes? Does it happen at the start of the day?
Does it only happen on a Tuesday?
Tuesdays are the worst days.
They're the worst.
Yeah.
Totally.
Is it happening only sporadically and you haven't quite figured out what it's aligned to or if it's aligned with something else that's happening? And lastly, what is the size of the problem? What is the extent of the problem? So my backups are running slow is a problem description, but not a very good one. My backups are now taking 5 hours is better, but my backups are taking 5 hours when previously they took 3 hours, makes it very clear that something has gone, something has changed. Something is now slower than before, is quantified, and that will help you reason about what that might be.
In fact, you don't want to just summarize what is happening, you want to make sure you summarize what is not happening. I wish to draw your attention to the curious incident of the dog in the nighttime. But the dog did nothing in the nighttime. That was the curious incident. The fact that the dog did nothing indicated an absence of something. There was no person there, they would have barked. There was no alert, therefore our disk did not completely fill up, right? What didn't happen can tell you as much as what does happen. Now we're talking about all this data that you're supposed to gather. What is this data? What kind of data is important? Well, there's nothing like firsthand evidence, and most important about this firsthand evidence is also that it be objective rather than subjective. Subjective is users are complaining that queries are maybe running slower. That's kind of secondhand and subjective. More objective would be our monitoring is reporting that average latency is now 50 milliseconds instead of 30 milliseconds, or we have log files here that show a query that takes almost a full second, and it's not supposed to, right? These are all objective facts that are very useful when discussing the problem. Now, where might you find a lot of such facts? Well, as Joanna already mentioned, there are a lot of metrics in Atlas. Like, there are so many metrics in Atlas that I lose track of them, and I go back a couple of weeks later, and oh my God, there's an entire new screen of metrics.
There's more and more graphs.
More and more graphs every day. And here's the other cool thing about them. It's not just metrics that show you what is happening right now, but it's the same metrics over time. So you can see this is how it is now, this is how it's been the last 24 hours, 48 hours, 1 week, 1 month, 6 months, etc. So maybe looking at some specific examples would be good here, right?
Yeah, let's go through a few examples. So the first one we're going to call a case of identity. We have our general problem description. Our queries are getting slower, but that's not enough. So we're going to ask some more questions and get some more data. We want to know when it started, and it started today around 7:30. Next, we want to know where. So where are these queries slow? They're on the primary node because that is our read preference. We only read from the primary. And lastly, we want to know what the extent is. Our queries are taking several seconds.
That's slow.
That is slow. Usually we would ask, what happened before, how slow was it before, but queries taking several seconds is a bit too slow. So what we want to do is now to look for more data, and especially useful is we know when the problem started. So we want to look for maybe something that changed around 7:30 when we started observing that queries were also getting slower. So maybe there are more queries now. If there's more query load on your system, each query might end up waiting for previous queries to complete and are now taking longer to complete. And if we look at the query metric, we can see the number of queries is fairly flat. There's no significant increase in the number of queries, so I don't think that's a reasonable path to go down. What else? Queries might be slow because we're scanning a lot of documents now. If we're scanning more documents than we were before, That's going to take longer. So is that the case? We have a query executor graph, and the green line there is the number of objects that are scanned for our queries. It's pretty spiky, but there's no real considerable change in load. That metric starts at 6:30 and ends at 8:30. So at 7:30, looks about the same as it did before. So I don't think that's the case either. We might be scanning a lot of documents, but if we're now returning a lot of documents, if we're returning more documents than before, maybe they're reading from disk. If we're scanning documents, but they were all in cache before, that's pretty fast. If we now need to go to disk to read them, that's going to take orders of magnitude slower. So let's look at the disk IOPS, the disk input and output operations. We can see that there is a spike, but not at 7:30, at about 6:45, 45 minutes earlier. Could a spike 45 minutes before we start seeing slow queries be correlated?
No.
No, I don't think so. And if we hover over that, we can see that the green line there, where we see the spike, is actually write operations. We've had an increase in write operations, but the read operations line is the blue line, and that is very close to 0. So I don't think that is the case either. So maybe we're scanning a lot of documents, but we're not returning many of them. Let's have a look at how many documents we're returning on average for our queries. And again, that blue line is fairly constant. So if we're scanning a lot of documents, it looks like we're returning a lot of them too. And we have a different graph to calculate the ratio, so you don't have to do your own maths. The query targeting graph shows you the ratio of the documents that you're scanning versus the documents that are being returned by your queries. And here we see the ratio is pretty good. It's fairly close to, it's very low. And we see one small spike, but also not at the time that we expect, and definitely not consistently. So unfortunately, I don't think that's it either. Well, what do we know? We know that our queries are getting slower, so we must be doing more work somewhere. So what else could cause a query to do work? Well, maybe we're doing in-memory sorts. Typically, if you do a query and you need the output to come in a specific sort order, ideally you would have an index. So you can read documents from that index, and as you find matches, you can just return them, and they're coming out in the right order. If you don't have an index to support your sort, what needs to happen is that you're scanning all of these documents, you're putting them all into memory, and then sorting them in memory. So let's have a look. We have a metric for this too. And look at that. There is a spike about exactly the same time we thought that
Bingo.
we thought that our queries were getting slower. So something must have changed, because there's now these in-memory sorts.
But wait, but the customer insisted that they didn't actually change anything at 7:30 in the morning.
And that's true. Customers always insist that they haven't changed anything, but maybe they didn't know. We do have a lot of customers where a pesky developer, Asia, a pesky developer has pushed something without telling the DBA, and the
That's
DBA...
also me. I go, how could you do that? I forgot I did that. But actually, there are other theories, right? It's possible that rather than the code changing and them suddenly doing sorts when they didn't used to, it's possible that there used to be an index to support this sort, and maybe that index got dropped.
Or hidden.
Or hidden. There's a new feature, it's relatively new, like in 4.4, where rather than dropping an index that you think you no longer need, you could hide it, which means that the query optimizer won't consider it, but the index is still actually there. That way, if it turns out you were wrong and that index actually was very necessary, it's much quicker to unhide a hidden index than to go ahead and have to rebuild the index from scratch.
Especially if the index building is at the same time as your normal query load. Your normal query load, which is now much more efficient than before.
Yeah, less efficient. Yeah.
Sorry, much less efficient than before.
Yes. And it's funny, actually, how many performance investigations kind of reach the same sort of conclusion, which is you need an index, or you need a more efficient index, or have you heard of indexes?
You need to read it.
All right, well, I have a case too to show. This was a real-life mystery. Things were getting slower, and there were no specifics like starting at 7:30. It was just things were slow, and like they didn't always used to be slow, so we don't know what's wrong. Please help us figure it out. I said, okay, well, let's look at a whole bunch of charts that you have. some of which you've already seen discussed in detail. And I specifically always like to hone in right on that query targeting. Query targeting basically says, how much work are you doing relative to how much work you're getting out of the database, right? If you are looking at 1,000 documents and then returning one of them, that's not a great ratio. So if we zoom in on this, hopefully you can see there's actually two lines. The blue one is how many index entries are we looking as a ratio to the number of documents being returned. The green one is how many actual documents we're looking at as a ratio to the number of documents being returned back to the application of the client. And this ratio seems to be hovering somewhere between 3,000 and 4,000, and that is not good. Generally, you want to look at one document in order to return one document. That's a good ratio. 3,000 is a lot bigger than 1, so that's a bad ratio. So, say, I wonder if we could see exactly what's going on the system that they have such bad ratio. And for that, we can go to the Profiler tab, where we see a whole bunch of orange pips and other different colored pips. As soon as the slide advances, normally what you see in the Profiler tab are slow queries, ones that are slower than the certain threshold. And by default, you'll see the time that each query is executing. But there's a little pull down there where it says display, where you can actually select to see specifically a plot of examined to returned ratio, for instance. Now, each one of those dots corresponds to an entry in the logs. And if you click on it, you will actually see that log line in detail. And here it is in JSON format. You probably can't see that, so don't squint. I will show you a blow-up of the relevant parts. First thing, no surprise, the plan summary turns out to be a collection scan. So if every time you need to find some documents, you have to scan your entire collection, that's not very efficient. In fact, this shows us we examined a little over 230,000 documents in order to return one. Now, in the grand scheme of things, a collection that only has 230,000 documents is actually a pretty small collection, right? But if you're usually searching for a single document to return and you have to look at that many, actually, collection itself might be bigger than that. That's just how many you looked at before you found what you wanted to return. Plus, people usually have many collections, right? Pretty soon, you're looking at a lot of data in order to return a pretty low number of things. The other thing we can see in the same log line is a bit of information from our storage subsystem. And the storage subsystem, the WireTiger cache, told us that it actually needed to read in a whole bunch of data into the cache in order to even service the query, right? And
that is a lot, Asia. That's 690 megabytes?
Yeah, that's a lot of data to read from disk into the cache, and it shows you the time reading micro. And frankly, what's happening is when you read stuff into the cache, it means something else has to get pushed out of the cache, right? So now we're starting to get an idea of why the queries are so slow, right? They're probably waiting for things to read into the cache, other things get pushed out of the cache. But now the customer says, but wait a minute, but we didn't change anything. Why are things so much slower now than they used to be? And for that, we're going to go to the DB Stats tab. And that tab shows us a bunch of stuff about the data size and index size. And here you can see that's 1 week's worth of data, which is not very much. But I zoomed out to 1 year's worth of data. And now each screen here is on a per database. So I looked at only a couple of the databases. They had over a dozen. And here's what I saw over the last year. Neither of these databases are very large, but they are both growing. And what that means, and this was only like an M20, pretty small instance. What that means is that a year ago, or whenever they deployed things, everything fit in RAM, everything seemed kind of fast, or at least fast enough.
They just didn't notice.
Yeah, they didn't have indexes, but they didn't notice. Because as things got bigger, not having those indexes or not having correct indexes became much, much more costly, right? And so that line, as the data size goes up, the cache stays constant. Now, what could they do? Could they just upsize to the next bigger instance and get more RAM? Yes, they could.
Maybe if you had infinite amounts of money
That
and
would be
very
very-
deep pockets.
That would be very profitable for MongoDB Atlas. It would not be very good way, because basically they would take a system that's inefficient and run it on bigger hardware. It would still be an inefficient system. The correct thing to do, well, you know, the theory anyway, is to create indexes, right? So our hypothesis is they need indexes to get their performance to be good. How do we validate this? Well, create the indexes and watch performance. Of course, they are the ones that have to do that. How do they know which indexes to create? There's a bunch of ways, right? They could open a case with technical services engineers who would probably give them advice looking at some logs, or they could go to the Performance Advisor tab, where there might be a suggestion of some indexes, and the create index suggestion always shows the queries that would be improved by the suggested index. There might even be a suggestion about dropping redundant indexes. Now, I know it seems like the answer to every performance question is create index, create an index.
It really isn't.
It really isn't. Indexes are not free. You shouldn't just go and create every possible index you could possibly think of. Indexes require maintenance while writing. Every time you write, any changed values that's indexed needs to be updated in the index. So you also don't want to have so many indexes that the query optimizer goes, oh my God, I have to evaluate 40 different indexes that all might help this query. So you want to have necessary indexes, but all of the indexes that you actually need. Yeah? Yeah, so it turns out that what is out of the common is usually a guide rather than a hindrance. And what does common mean here? It means normal, right?
Right, you need to know what your normal behavior is, right? If you know what your normal behavior is, you can then look to see if something has changed, if something is out of the normal, if something is out of the range that you normally expect. Because if you don't know what you expect, how do you know when a value is actually abnormal for your system? Let's go through an example. Upload gigabytes per hour. Quick recap for anyone who isn't familiar with replication. Every time that you do a write to a replica set, you write to the primary node. That write gets put into an internal system collection called the uplog, and the secondaries read those and replicate those writes from the primary's uplog. So the upload gigabyte per hour metric is a metric about how much write load your system is under. So here we can see that the upload gigabyte per hour metric is fairly constant. So this is normal, right? Maybe, maybe not. For some customers, this would be normal. For some customers, this would be a very, very high write load for their system. For other customers, this is very low. Something must have gone wrong. Maybe one of my app servers is down. So if we zoom out, wow, there's been a huge change in upload gigabytes per hour. It was at 50 gigabytes per hour. And then at about 1 p.m., it suddenly started growing, and now it's at 150 gigabytes per hour.
Something's wrong.
Something must have gone wrong, right? And I must admit, this was my ticket. I did think that something had gone wrong. I jumped to a conclusion. Don't do that, because if I had zoomed out, I would have seen this is actually pretty normal. This is just a normal load. You can see that on a weekly cadence, the upload gigabytes per hour goes up. Maybe people are waking up from the weekend, are starting to do some work, and then at the end of the week, it starts dropping down again for the weekend. So no 2 weeks look alike, of course. Every week is different, but the trend is there. On a weekly cadence, the upload gigabytes per hour goes up. At the end of the week, it goes down. So the huge spike that I thought I saw that indicated something was abnormal is not abnormal at all. It's just a normal Monday morning workload.
Yeah, so it's of the highest importance to be able to recognize out of a number of facts which are incidental and which are vital. Right? It was incidental that the load increased. It was incidental to the fact that it was a Monday morning.
Correct.
What is vital is when things are not normal according to whatever is normal in your system.
Right. There are so many metrics in Atlas that you can't think to look through all of them every time you have a problem. You need to be able to understand what you expect to see, which is part of normal operations, so that when you look at these metrics, you can see what looks strange, what looks like it's out of bounds for what you expect.
Yeah, so solving puzzles like this, is it as much fun as being Sherlock Holmes and detective?
I think so.
Yeah, I think so too. I think so too. I think what we do is my favorite quote from Sherlock Holmes, which is, we balance probabilities and choose the most likely. It is a scientific use of imagination. So we thank you all for coming.